Yeah. And then many thanks for invitation. This is great that this seminar is organized. So today my talk is concerning neural networks, and the aim is to develop a little bit new type of neural networks that are engineered to solve nonlinear inverse problems. The alternative title of this talk is that how to use the uniqueness results for inverse problems to design neural networks. And I wanted to emphasize this thing because in our community, like many theoretical results, they could provide a recipe how to build up neural networks. And all these results are done in collaboration with Christopher Wong and Martin de Hoop from Rice University. So I'm going to consider inverse problem for wave equation, mainly in the one-dimensional case, but to formulate this in multidimensional case, we are going to consider this wave equation, where the wave speed c of x, and we assume that at time t is equal to 0, the wave and its time derivative are 0, but on the boundary, we have a boundary source that is modeled by Neumann boundary condition. So the Neumann boundary value h physically corresponds to boundary source, like here in this picture. If you are doing like seismic imaging, the source is provided by these air guns that produce an acoustic signal. Then it propagates and to unknown medium, some portion of the signal reflects back and we record it on the boundary. And this gives us the Neumann-to-Dirichlet map or to source to solution map that maps the source that we can control and that we produce ourselves. It maps the source to the boundary value of the wave. So the acoustic wave here in the surface, like in this picture, is measured by these microphones in this streamer. Now traditionally our community denotes Neumann-to-Dirichlet map by lambda c. But when I have been discussing for machine learning community, this has been a huge confusion because lambda often denotes them a parameter or something like that. And for us, it is the data. We consider it as a variable. And that's why I ask your patience to somehow that I will denote it now by non-standard notation. So the Neumann-to-Dirichlet map is y. And c here indicates that it's related to some wave speed function c of x that is unknown. And in particular, we are going to consider the one-dimensional problem where there's like the space is one-dimensional, and the aim is to use neural networks to solve this problem. First, few words about the history. So the one-dimensional problems were extensively studied on 50s and 60s by Gelfand, Levitan, and Marchenko. But the multidimensional problem was studied on 80s, especially the inverse problem for equivalent to wave equation, and inverse problems for that was studied by Nachman, Sylvester, and Ullman. The main topic of my talk is related to boundary control method that can be used for reconstruction of a time-independent metric that was developed by Belishev and Kurilev together with Tataru's unique continuation principle. In particular, we are going to use a modified version of this, so-called modified time reversal method that we developed with Bingham, Kurilev, and Silta. And quite recently, this has been quite successfully numerically implemented by Martin de Hoop, Paul Kepley, and Lauri Oksanen. And I also want to mention like this kind of more theoretical developments for like combining several measurements together, as we did with Helin and Oksanen, partial data problems with Oksanen, and that was nicely generalized by Mansouri and Milne. Then for problems with lap first order perturbation was studied by Kurilev, Oksanen, and Paternine. And then there's also a method that is a kind of sister method to boundary control method, so-called scattering control method that was developed by Kadey, de Hoop, Kat Nelson, and Ullman quite recently. So this is the goal of this talk, what we are going to do. We are going to study inverse problem for wave equation in one-dimensional case. Actually, many of these neural network constructions that I'm going to consider, they work also in n-dimensional case. I would say that at this moment, the analytical part of the method goes nicely through in a higher dimensional case, but the geometrical part now at this moment requires that we consider one-dimensional case. For this, we are going to use one particular, this kind of constructive and rigorous method. I call this kind of rigorous methods as analytic methods, which means that we have explicit formulas. And that is the boundary control method developed by Velis and Kuril. And we use its regularized version that we studied here in this paper with Bingham, Kurilev, and Siltanen. And recently we have somehow continued regularization with Korpela and Lauri Oksanen. So we consider the solution operator, or solution map, the nonlinear map that takes in the Neumann-to-Dirichlet map and maps that to the wave speed. And here we already somehow see one difficulty. The data that is given to us, the Neumann-to-Dirichlet map, it is a linear operator. So we have to consider a new type of neural networks. I say that we propose an architecture of neural networks where input is a linear operator. Then we are going to show that this analytical method, given by boundary control method, that can be written as a neural network with this proposed architecture. And now we have a family of neural networks where one particular element of this family is the method that has been rigorously analyzed. And because of that, we can train neural networks, and because there is this analytical method given by uniqueness results for inverse problems, we know that it works as well as the analytical method. So we can analyze the performance of the trained neural networks by using the stability theorems for inverse problems. So this is where the theory of inverse problems come into the play. We design the architecture so that it imitates rigorous methods given by proofs, and also we can then use proof to analyze neural networks. And let me now go to one-dimensional inverse problem. So problem where like this type of seismic imaging problem is replaced by a very simplified model where the space is one-dimensional. So we have a line where we have signals that propagate to unknown medium, and something is reflected back, and we are measuring the wave and want to find the speed on this unknown portion of the line. So let me recall the setting in one-dimensional case. So the space is now just a positive real axis, and x is so element of this space. And this corresponds to the subsurface imaging when the wave speed depends only on depth. So this is a simplified seismic imaging problem. We are going to consider the inverse problem for wave equation. Here is the one-dimensional wave equation where space is one-dimensional. So it's actually 1 plus one-dimensional. Both space and time are one-dimensional. Again, the wave vanishes at time t is equal to 0. There's a boundary source given by the Neumann boundary value or the derivative at the one boundary point, the function h. And the wave speed c of x is unknown. To emphasize that waves are produced by sources, I denote this solution u by u superindexed h. Is this source h, this boundary source, the Neumann boundary value that produces the wave. Then when we have some finite time interval through measurements, we have interval 0 to 2t, and there we define the Neumann-to-Dirichlet map. And I recall now that this Neumann-to-Dirichlet map is denoted by y. So yc is the Neumann-to-Dirichlet map for this equation. So this corresponds to boundary measurements with unknown wave speed. And this operator is linear operator or a matrix. And physically, it maps the boundary source to the boundary value of the wave at the boundary point, x is 0. So this is the problem that we study. This is a very geometric problem, and it's very useful to consider travel times of waves. How is the travel time of waves from boundary point 0 to point x? So it measures how long time it takes from the waves to go from boundary to given point x, and it is given by this integral 1 over wave speed, and you integrate that. This is actually can be also considered as a primary object in one-dimensional case, because if we can construct in some way the inverse of this travel time function, this is a kind of a function that maps time to depth, this tau inverse, if we know this tau minus 1, this time inverse of tau, then we can determine the travel time function tau, and then we just take this equation here, differentiate it, and manipulate it a bit, and we can find the wave speed. So because of this observation, I'm now going to consider only the reconstruction of the inverse travel time function, also determines the wave speed. So our inverse problem now is to to construct the inverse travel time function when the boundary measurements are given. We consider actually these boundary measurements, this linear operator y as a variable, and we consider a function that maps the boundary measurements to the inverse travel time function. So that maps the linear operator to a function. And our goal is to construct a neural network that approximates this function here. But first I want to explain the traditional way to solve the inverse problem. What is the analytic method to solve inverse problems? So this is the crash course to boundary control method in one-dimensional case. So we first show that the Neumann-to-Dirichlet map determines the inner products of waves. So we consider two waves, UH and UF, at time t. And their product, we multiply them together at time t is t capital, and then integrate over x variable. And we integrate it by using this kind of volume that makes the wave operator self-adjoint. So this is a little bit non-physical. It's very physical, but it is non-standard volume. So this is the definition of the inner products of waves, and the norms of waves is just that is the inner product of the wave with itself, and then we take the square root. Now there's a very important result by Blogovetsky, so-called Blogovetsky formula, which says that we can compute the inner products of waves using only boundary information. So what objects appear here? So this ky is a special operator that involves the Neumann map to us as a data, and then a few simple operators. And these two simple operators are the time reversal operator, and then this integral operator, explicit integral operator, that I call a low-pass filter. So these R and J are very simple operators. Y, the Neumann-to-Dirichlet map, is given us as data. So we can, from boundary data, we can find this operator K, and here are just boundary sources that we integrate in this way. This gives information on the boundary that gives the inner product of two waves. Also, it is easy to integrate, like what is the inner product of wave with a constant function y. These are the main formulas that connect the boundary measurements and boundary data to things that are in the interior of the manifold. In the first version of the method by Bingham, Kurilev, and Siltanen, and we also modified it a little bit with diff hoop and Wong, is that we can solve the inverse problem as follows. We do two steps. Let me now go through these two steps that solve the problem. Where in these steps we assume that we are given the Neumann-to-Dirichlet map y. The first step is that we consider different depth parameters s. So we consider waves that propagate time s to interior of the manifold, or sorry, to the interior of the unknown space. And then these special boundary sources here, this h beta s, where beta is a regularization parameter, let them be the solutions of this minimization problem, where we minimize the L2 norm of the wave -1, plus then a regularization term. A here is some isolation in the finite basis, but important here is that we use here L1 norm. And now because these inner products and inner products with function 1 can be computed using boundary data, this function that we minimize here can be computed using just boundary information. This here. So here we have this ky operator that involved this Neumann-to-Dirichlet map and some simple operators. And then there are some other explicit things. And this minimization is considered over all sources that are supported on time interval t minus s to s. So they are supported on an interval which length is s, so they can propagate like to travel time s from the boundary to the interior of the unknown space. Then one can show that because like this part here, this tries to force the value of the wave to be as possible. Then we can show that when regularization parameter beta goes to 0, then the waves produced by these sources that are solutions of this minimization problem, they are such that they are 1 up to the travel time s from the boundary and 0 otherwise. And we call these the optimized solutions because they are obtained by solving this minimization problem. And how we do in practice, we don't take limit beta goes to 0, but we compute these waves. We consider the sources actually and compute the waves when beta is small, and then the sources that we have found by using minimization are such that they produce waves that are almost 1 in this interval and 0 otherwise. So in this solution method that is rigorous, this has 2 steps. This was the first one that find these optimized sources by the minimization problem. The second is then that we use them by using very simple algebra. We integrate these optimized sources with function t capital minus t. These actually turn to be the same as the inner products of the waves with function 1. And because these functions, beta s, these are almost 1 in interval 0 to tau minus 1 s. These inner products are very close. When beta goes to 0, they actually go to this. They are the volumes of these intervals, and they are these explicit integrals. So now from the optimized sources, we can compute these integrals that involve, for instance, unknown wave speed and unknown travel time function. Then we take these volumes, differentiate them, and then a simple manipulation gives us this inverse travel time function. Also, those give the value of the unknown wave speed time coordinates. So there are 2 steps. First, we solve optimization problem. Then we do some simple algebra that was here. And how this is now related to neural networks. Let me go back to this minimization problem, that is mixture of L2 and L1 like minimization. And these can be solved by using iteration. So this kind of like L1 regularized minimization problems can be solved by using so-called soft thresholding iteration. And actually in this formula, it is not so important what exactly is here, just the form of this iteration is important. We start from some value, then we iterate at each step for this function h that we have produced. We operate with a combination of this operator y operators, and then we add some like basically constant term. And then we use the soft thresholding operation. The soft thresholding is like an element-wise operation that moves all values closer to value 0. And it is somehow written here. And to imitate the neural network theory, I write the soft thresholding operator in combination of so-called ReLU operators. I return to this to the later. But ReLU operators are component-wise operations where we take maximum of value x and 0. And these are very much used in neural networks. So the step 1, that was solution of minimization problem. We can approximate this by doing L steps of this iteration. And after that, we just substitute the result to a meromorphic function and do some explicit computations. And those give the values of the inverse travel time function, the grid point that we are interested in. Okay, so this was now the story how you solve, how you use like this kind of like uniqueness results to get a constructive algorithm that solves the inverse problem. How we are going to use this? So let me recall how this can be somehow written in a little bit different form. We are going to consider this map that maps boundary measurements to inverse travel time function. So they map a linear operator y to a function. And we can write this in the two ways. First, we consider maps, here these f functions, that map the boundary measurements to optimized sources. And when I have obtained the optimized sources, then I just make some meromorphic operations to define a function fy. And this gives this inverse function. Now our aim is to define a family of neural networks that we call operator recurrent networks that approximate these functions, that map the boundary measurements to optimized sources. And this is a new type of neural network because it takes in a linear operator. Then we take these results and insert them to a function, explicit function. These explicit functions can be approximated by standard neural networks. So because f's and g's can be approximated by neural network, also this capital F can be approximated by a neural network. Let me now define what type of, let me go to jump to a new topic. Now I give a review on neural networks, and then I introduce what type of new neural networks we are going to consider. So now we go to this type of standard pictures of neural networks where we have layers, we put data, and the data is propagated through these layers to some final result. And so all these somehow propagation from layer to layer, they are linear. And in each node, there is some nonlinear operation called activation function. And nowadays in theory of neural networks, like the very standard is the most commonly used activation function is so-called rectified linear unit. That is component-wise. But let's now just first think a single component. So the ReLU function is maximum of 0 and x. So when x is positive, it gives x. If x is negative or 0, it gives 0. So these are the ReLU functions. They are very much used because they make the minimization algorithms relatively like simple. By the way, now when I go to these neural networks, please interrupt me if you have any questions or concepts that are omitted that you would like to hear. Okay, let me like to fix some notations. Let me somehow write this more precisely. So a standard neural network or an additive neural network is a function that maps vectors to vectors, so that when we want to compute what is f theta of x, so theta denotes all the parameters of the neural network. So we start from the layer 0, where we just put data. And then we move, let me go back to this picture, we move from 0th layer to first layer, from first layer to second layer, and so on. So each somehow moving, when we move from one layer to other, we make an affine operation where the output of layer L, we multiply it by matrix, add some vector, and then we use activation function. The function is the rectified linear unit that is component-wise. So here it is written for a matrix, for a vector. So all elements of the vector, we somehow remove negative values by replacing them by 0, and all positive values are kept as they are. So small l here denotes the index of the layer. Maximum depth is L capital. HL are the vectors in the output of each layer L. Then we have these matrices that are called weight matrices, and vectors B's that are called bias vectors, and they depend on parameters theta in some way. And this is the standard neural network. Actually, this has been extensively now used also in inverse problems. There was a very interesting paper by Adler and Öchten, where one used it, wrote a modified gradient descent method by using. Then I want to point out like few like review papers. One is by Unses group in SIAM review, where they explain how splines are related to neural networks and how one can use these neural networks for linear inverse problems. Then there's other review paper by Aric, Maas, Öktem, and Schoenlieb in Acta Numerica, which somehow like combines regularization theory and neural networks. Then recently, quite this type of like popular neural network, so-called GANs and Neumann networks have been used to inverse problems. And I want to somehow also mention some explicit applications. So these were more for theory. The applications, diffusion problems, especially by Aric and Hauptmann. Also in Helsinki, we considered electrical impedance. We considered electrical impedance tomography, and we have also considered limited angle tomography. And then for different types of scattering problems, there are a very interesting paper by Ullmann and Jiran Wang, like considers nonlinear problems using neural networks. But all these papers here, they concern this kind of additive neural networks. Now we are going to modify this. So what is the modification that we do? Let me recall that the standard neural network that I had a few slides ago, they were functions that take in vector, and then they compute like iteratively the following operations, where we somehow like in each layer we have affine operations. We multiply with the matrix, add a vector, and then we use the activation function. Now for us, the data is given as a linear operator. So we want to emphasize this fact that the data has a form of linear operator, and we want to use it as a linear operator. Instead of somehow considering neural networks that map vectors to vectors, we consider neural networks that map a matrix or a linear operator to a vector. So they take in a matrix, and then they compute this kind of iteration where y here is used as an operator. So our operator that is given to us as a data, like the Neumann-to-Dirichlet map, it is affine steps. We somehow operate with y, then we operate with weight matrix, and then add some bias vector. So this is the new type of neural networks where data is considered as a linear operator in each layer. Okay. Let me next define this in a little bit more general setting. Then I somehow make this connection to theory of inverse problems and consider how this like the theory of inverse problems can be used to estimate how these neural networks work. So this is the definition of the neural networks that we consider. We call them operator recurrent network with depth theta. They have width n, and then the parameters theta are in some huge unit cube. Then we define that these neural networks, they are functions that map a matrix, n times n matrix, to a vector, and they are given in the following way. We start the iteration from some fixed point that is given as a, we have a first bias vector. That is we put here in the input of this neural network, in the 0 step of the neural network. And then when we iterate in this neural network, we go forward, we go layer to layer. Then we use affine operations where the data operator y operates to the output of the previous layer. So here is just affine operations. Here is similar type of affine operations, and here we also have this activation function, the nonlinear activation function that are in this talk always the rectified linear unit functions. So they component-wise remove negative components of the vectors and replace them by 0. So the initial vector H0 is independent of the data that is given to us. The weight matrices and the bias vectors, this weight matrices A and bias vectors B, they depend on parameters in some way. And here it is how visualized in here. So the data operator is given to us as input. So here should be actually y, not lambda. This is used in each step as linear operator that operates to outputs. So why this is interesting? Let's recall the earlier analytical method, the boundary control method. There, the optimized sources were obtained by doing L steps of soft thresholding iteration. The soft thresholding is practically the same as ReLU. And inside these soft thresholding operations, there we have this type of like operations where we have mixture of operator y, that is the Neumann-to-Dirichlet map, and then some simple operations. So R here was if you somehow write things in finite basis, R is the matrix of the time reversal operation. Pj is some projector that tells that what is the depth, how deep we are probing the medium. J is a low pass filter, and B is some constant vector. And then there was some regularization parameter. So this here has very similar structure as this. Actually, we can take this iterative soft thresholding iteration that is used in boundary control method, and just slightly modifying the notations, we can write it in forms of this operator recurrent network. So our analytical inverse problem solution method can be written as one neural network of this type. That's the whole idea of this talk, that the analytical method given by uniqueness proofs can be written as a neural network. And then are going to study this family of neural networks that contain also this rigorous operator that solves the inverse problem. Okay, so like here now we have different explicit matrices, and here we have these weight matrices and biases that depend on parameters. Let me describe what type of dependency on parameters we want to use. Here is what we do. All these weight matrices, they have two parts. One is a fixed part, and one is a sparse part that depends on parameters. And these sparse matrices, they are written in terms of almost like singular vectors. So the singular vectors multiplied by singular values, those are theta vectors, and these theta vectors, they determine this matrix is A1. This index 1 as you know as a super index. So we have some fixed operators that don't depend on parameters, and then we have some sparse matrices that are determined by the parameters. So how we take the rigorous algorithm and transform it in a good way to neural network? We do the following. All compact operators in the analytic method, for instance, this low pass filter, J, this is a compact operator, that is replaced by a sparse matrix. So all the compact operators are replaced by matrices that depend on data, and then we somehow start to like change these operations. We are learning them optimal such matrices by using the data. Then the analytical method also has some non-compact operators. For instance, there's identity matrix or time reversal operation that are like they cannot be approximated by sparse matrices. So then we keep them as they are. So these components that correspond like identity operator, they are not learned, but they are determined by the analytical method. So let me go back. So this was the analytical method. Here is like I operator. We keep it as it is. Here we have operator J. So we replace that with a sparse matrix that we try to learn and optimize so that it would somehow produce as good reconstructions as possible. If a recipe, what type of like neural networks we consider, then we replace all compact operators here by matrices that we try to learn from data. Okay, let's go to this. So we want to consider this kind of sparse matrices, and the parameters now correspond to the singular values of these sparse matrices. Okay, how we do this kind of sparsity? We use L1 regularization. And now I changed it a bit the gear. Instead of considering only the solution of inverse problem for wave equation, let me consider a general target function. It could be somehow the solution operator to some other inverse problem, for instance. The point is that it maps operator n time n matrix. It maps to a vector, and we want to approximate it by using neural networks. So we want to find some parameters theta, so that the neural network f theta. So f theta now means that we have a neural network, theta are the parameters, that approximates the target function f. I apologize, the notations may be a little like strange because like f and f theta looks very similar, but this is the standard way of writing these things in theory of neural networks. So f theta is very different than f. F is the function that is our target function that we try to somehow approximate, and f thetas are neural networks that we construct. So to somehow do training, we need to have some function, a cost function that we optimize. And for that end, we use the regularized loss function L with the regularization parameter alpha. And we use this loss function here. So it has two components. The first component, this L2, this norm to power 2, this measures how well the neural network approaches target function f. And then we have a regularization term alpha times regularization that tries to keep this neural network as simple as possible. To make this learned components of the weight matrices sparse, we use a L1 norm. So we take these singular vectors or the vectors, they compute their norm, and then compute the L1 norm of these norms of these vectors. So this actually is this kind of mixed 1-2 norm, but to keep notation simple, I consider this as one norm. So this is the notation that I use. So this one norm makes like that the solution of the minimizers of this cost function, they will be sparse. So this is what that forces the sparsity into the model. And the sparsity has a huge consequences how much we need to have data for training. That will come later. So how we do training? Now we assume that we have some like these linear maps that are given to us. This is random and follows some a priori distribution. I denote it by this, that mu has the distribution, y has the distribution mu. So I use this notation. So if you could solve range characterization problems for inverse problems, then this mu would be supported on the space of all Neumann-to-Dirichlet maps. So, but we can somehow numerically compute lots of samples that are Neumann-to-Dirichlet maps. That's what we do. We assume that we have independent samples from this distribution, y1, y2, and so on, yn. So we have n sample elements. And we assume that for all of those y1, y2, and so on, for them we know what is the value of the target function. So we now have the training data that consists of these operators y and the values of f at point y1, y2, and so on. So in practice, this is done by using simulation where we have lots of different wave speeds. We simulate, take random wave speeds, then we simulate like what are the Neumann-to-Dirichlet maps for those, and then we have the pairs of the boundary measurements and then the wave speeds. This is how we do this in practice. But this is the abstract formulation. Now to train the neural network, this means minimization with minimization of the empirical loss function. So when we have this training data, then we can compute this type of empirical loss, that is just the of all these errors, how well the neural network approximates these values in the training data. And then we add there the regularization term, alpha times like the L1 norm of the parameters. So when we are given the training data S, then we can compute for any parameter value theta, we can compute this empirical loss function, and then we can solve this minimization problem. So this theta s, this is the optimizer with this of this empirical loss function. In this talk, we just assume that we can find the minimizer. In practice, it is very difficult question that if this loss function has a local minima, how we actually find the minimizers. But now I assume that we can compute it in some way. So this is how we somehow train the neural networks that solves inverse problems. This is the recipe how to somehow use training data to obtain some neural network. To analyze how well this works, we also have more theoretical concepts. There's also for any parameters theta, and so that we have neural network f theta, we consider the expected loss. This is the expectation of the loss function. Let me go back to the loss function. So this was our loss function. So when we consider the expected loss, we take this theoretical loss function and we compute this expectation. So this is very similar to empirical loss function if we would have infinite amount of data. Then the parameters that minimize this function, so theta star, that are the parameters that minimize the expected loss, and we call that optimal neural network. So if we would have infinite amount of training data, actually we would have all possible elements that we are interested in, then we could compute this expected loss, and this parameters value theta star, those give the best possible neural network that we can use to solve the problem. This would be the optimal neural network that we would like to construct. But we have finite amount of data, so we have to compare how close this optimal neural network, how close it is to this empirical value that is computed by using finite training data. Those we are now interested in. So this is one of the points of the talk. This is trivial observation, but it tells that how inverse problems, the theory of inverse problems, can be connected to neural networks. Let's assume now that we have some deterministic method to solve inverse problem, for instance, the boundary constraint method, and that we can approximate it well with a neural network that has certain parameters theta 0. Then we have this trivial but important result that the optimal neural network is such that its expected loss is always less or equal than the expected loss of the analytical method. So this says that the trained neural network that we obtain by training, this works at least as well as our analytical method, but typically it works much better. So the analytical method gives us a recipe how to build up neural networks. This recipe is such that the neural network has lots of free parameters. Then we try to optimize all the parameters in the method so that it works in practice as well as it is ever possible. And it is usually it works better than the operation recipe that is given by uniqueness proof. So this just means that the optimal neural network has at least as good behavior, expected performance as the analytical method. So how to use this fact that we have some analytical method? How to characterize this type of methods? This is explained in this definition. We say that the target function f can be approximated with accuracy epsilon 0 by a neural network with depth L and sparsity bound R0 if there is some parameter value theta 0 such that the L1 norm of the parameters is bounded by R0, and then the neural network has good accuracy. This error, how well the approximates the true function is bounded by epsilon 0. And this is for an example how we can use this for one-dimensional boundary control method. With Korpela and Oksanen, we somehow proved that theoretical stability estimates that says that the one-dimensional boundary control method, that is explicit algorithm, satisfies these properties, where the sparsity bound is this epsilon 0 to power 16, and we also have the length, the depth of the neural network, and then the width is now horrible. It is z epsilon 0 to power minus 175. Why is this so bad? This is bad because the theoretical proof consists of many lemmas, and each lemma makes some estimate. These estimates in the lemmas are some optimal. So they are true, but they are not optimal ones. And when you combine say 5 lemmas with suboptimal estimates, then we multiply all of them together, and we get like relatively bad estimate. So it is very natural that there should be like better ways to make this kind of approximation, but this gives us some bounds. But anyway, the theoretical methods tell that there is some neural network, the one that approximates the boundary control method, that satisfies some sparsity bound, and this has some accuracy. Why we have this sparsity bounds? The sparsity bounds are here because the analytical method has some compact operators, and all these compact operators can be well approximated with sparse matrices. Okay, so let me go to these kind of theoretical results that tell that how well the neural networks behave. To evaluate the performance of neural network, we use 2 concepts. The first, the expected performance gap. That is actually that measures how well the trained neural network, with parameters coming from training data, what is its difference to the best possible neural network, the optimal neural network. So here is the performance gap. The performance gap is the expected loss when we have like parameters that are optimized from the training data, and here we have expected loss of the optimal neural network. This is, I would say that this is interesting for the inverse problem because it tells that like how well like the thing that the neural network that we have trained, how close it is to the best possible one. Then in the machine learning literature, they are more interested of the expected generalization error that measures the difference of the empirical loss function and the expected loss function. This expected loss function here, this is something that is theoretical. This empirical loss function is something that you can compute from your data. Notice that here this expected loss is the same as here. So that if we can estimate both of these quantities, then we can somehow compute that how close the optimal neural network is to the one that we somehow we can estimate this quantity here by using things that we can compute from the data. So this generalization gap measures how well we can estimate the performance of the trained neural network when we have only the training data and no other elements. So here are the results. First, this is just a pure approximation result. That if we are given randomly sampled training data, then the probability that if we take random samples, the probability that generalization is delta. This is very large. It's 1 minus something that is exponential. So here, when the number of samples grow, this starts to decay exponentially. But here are these C1 and C2, some constants, and then they actually tell that what is for how large values n we have to go that this estimate is useful. So that this 1 minus something, this is minus something is less than 1. And we can explicitly estimate what these constants are. And now we can use the fact that we can use theoretical results from inverse problems, namely, we can assume that there is some neural network that approximates the target function with accuracy epsilon 0 and sparsity bound R0. And then we somehow put here an estimate which says we don't regularize too much. Then we have the similar type of inequality, but it's going to change. Let me go back to the earlier slide. Here was the without any inverse problems theory, like that we could use. Here is when we have some good estimates. Here in the general case, like this alpha, for instance, is inside exponential. When we use the theory of inverse problems, we use this existence of epsilon 0 and r0. Here, this is just a, like power of alpha. So these estimates change their nature very much. These estimates are much better when we know that there is some analytical method. So this was the one part of the how we qualify how good the estimates, how well the neural networks work. This was the generalization gap. There was also this performance gap, and the performance gap and generalization gap estimates are almost the same. Only here is this factor 2 that has to be included here. Let me go back to this. I recall that we had two quantities gap that tells that what is the difference of the trained neural network to the optimal one. Then we have a generalization gap that tells that how well we can estimate from data these quantities. And now both of these can be like estimated quite well. And if we know that we have some, if we a priori know that we have solution method that provides good algorithm, this helps hugely, like these estimates, which tells that what is basically this tells that how much training data is needed, so that the neural network approximates the best possible neural network with reasonable accuracy. Let me finish with some practical results. These are actually very, very preliminary and like numerical like results. Here we had like wave speed. It is unknown. This wave speed corresponds to this this inverse of the travel time function, and this is the result that the neural network gives. I have to say that this was somehow done, like this was not yet very good numerics in the sense that here we didn't use the sparsity penalization at all. So the neural network has a huge size compared to what it would have if we add here like the sparsity bounds. But we haven't yet we haven't yet implemented the sparsity bounds. So the neural networks that we consider to obtain this type of quality of reconstructions, like they contain much more parameters that are necessary. But anyway, they somehow seem to produce at least like reasonable results. And thank you very much for your attention. These slides are on my webpage, and I put there like references also that you can like find more material on this topic. Thank you very much. I will now end. Thank you.
Thank you very much. Thank you very much. Thank you very much, Matti. Thank you. Are there any questions or comments? Please, are there any questions or comments? Sorry.
May I ask a question?
Oh yes, please, Jan.
Hi, Matti. It's very nice talk and very interesting. I just have a quick question on page 21. Is there a particular reason that you choose the compact operator to learn, but not the non-compact?
Okay, yes, that's a good question. Yes. So the point was now that it seems that in practice, when like people want to train neural networks, the number of parameters is actually a crucial thing. That's why for instance, convolutional neural networks are very popular, because when you have like small convolutional kernels, you have quite like few parameters.
Yeah. So that's mainly to reduce the number of parameters.
Now, if you want to learn, that's true. Yes. So yes. So that is one thing. Yes. So it is in practice we want to reduce the number of parameters. Also, the thing is that to obtain some estimates that how much training data you need. Like we use this kind of like estimates for this kind of tail event estimates that are very much somehow using like that. When you consider they use the volume of the parameter space. If we somehow consider all possible vectors or all possible full matrices, then the parameter space has a huge basically like Hausdorff dimension. But if we have a like we know that the parameter vectors are only like sparse elements. Then the Hausdorff dimension of the parameter space becomes much smaller, and then you can cover our parameter space with a small number of small balls, and this is very crucial when you say that how many training elements, so how many elements in training data we need to have, because, and that makes somehow sense that if we have a huge number of parameters to learn them, we need a huge number of data. If you can reduce the number of the parameters that we want to learn, then we also reduce the number of training data. And this is actually in these last two theorems that I showed. This is the explanation of why the estimates change their nature when we add these sparsity constraints in the optimization.
I see. Yeah. Thank you.
Thank you. Very excellent question.
Thank you very much. There are some other questions, so please ask. I mean, you can easily unmute yourself. Sorry.
Yeah, I have a question.
Yes.
Can I ask a question?
Oh, please.
Yes.
Yes.
Yes. So following that question, but it seems to me the compact operator is more ill-conditioned to learn. So because you're smoothing things. So when you learn that, it's maybe have few parameters, but the inverse problem of learning the compact operator can be more ill-posed, right?
Let's see. Okay, there's also one interesting thing is that when we think that we try to learn a neural network, we are actually not interested of the exact values of the parameters. So if we somehow just slightly change the training set, then the parameters that we find can be very different. So we are actually interested only that what is the total what is the final mapping that map when we map the input to the output should be close to the target ones. So that there might be a huge number of different parameters that produce almost as good results. And I think that so that actually I'm not professional thing in this kind of numerics of deep learning, but I think that if you somehow run like you do training with PIs and you make it just a small modification of your training data, then the parameter values that you get are very different. So they're when the thetas are not, there is not unique minimum for theta, that you can get very different values. So like in some sense the finding the parameter values is in this case very ill-posed problem, because but we are not interested finally of the the values of the parameter. We are interested how.
But it seems to me like to do a deconvolution, right? You have a convolution operator. You want to find the deconvolution. That's the compact operator you're trying to find. But that, to me, could be even in general, that's a very difficult problem.
Yes, so let's see. So the
may I offer a comment? I think it's the opposite of what you said. It's very easy to learn a compact operator because it has few parameters that completely describe. If you wanted to learn the inverse of a compact operator, that would be difficult to learn.
Yeah, but it is somehow very easy to somehow obtain lots of different type of neural networks that has the same output. Even if we think that all layers would be linear, so there would be no activation function. So if we first layer is identity operator, then the second layer is multiplied by a matrix A. That is one neural network. Then there's other neural network that is first multiplication by A and then identity, and they produce the same result. So like identity times A and A times identity. So in this sense, they are we are not trying to learn one particular neural network, but we are trying to learn like any neural network that gives good results.
Okay, thank you.
But an excellent question, yes. And thank you also for John for your answer. Like that, I think that in practice, you might be correct that we haven't looked how stable this is.
Yes.
We have very somehow fixed form of neural network. Maybe it is unique, and really, and like you said, that the sparse, it is much easier to learn sparse parameters than like full matrices.
Thank you.
Thank you very much. Are there any further questions or comments?
Okay, this is Rakesh, Matti. So I'm sorry, I have 2 or 3 questions, very elementary questions. I know very little about them. The first thing is, how is the dimension for each layer determined? You have the DL parameters. So,
oh yes, so it could. Okay, if I answer to this first, so now these neural networks that we study, for the operator recurrent neural networks, there the dimensions stays constant. One reason for this is that we assume that we are given a matrix that corresponds to the Neumann-to-Dirichlet map, so its size stays the same. So for us, like this size stays all the same. For general neural networks, this is something that they very much try to optimize, that they somehow vary these dimensions so that they could get good results. Like there are these famous like UNets, for instance, where where you try to optimize dimensions so that the results look well. But some people who do this very professionally say that there is a big element of alchemy in designing of the architecture of neural networks. So one of our goals was that we wanted to give a rigorous foundation. We wanted to give a rigorous foundation for a single type of architecture that we know that it surely should work, because we've just copied the methods that we are using in analytical theory of inverse problems. To somehow we took those methods and then we copied that architecture to neural networks.
So the second question, you mentioned somewhere in passing that we know that for many inverse problems, the minimization algorithms get stuck sometimes on local minima. Is that affect what you do? You mentioned something about that quickly.
Yes. So I think that this is a huge topic in theory of neural networks, that how to optimization works. Like this, they have these stochastic gradient methods that try to avoid local minima. So what is the efficient way to solve this minimization problem that you need to do when you are training the neural network? This is a very serious topic, and that we haven't touched so.
Okay, I have one more last question, then that.
Please. Oh yes.
Okay, so are there many theoretical results in machine learning training neural networks? I mean, like how well things approximate. Are there results like that?
Oh, so there are quite very interesting results in approximate theory. Actually, say on 80s, 90s, they studied lots of approximation results for shallow neural networks that only have one hidden layer, and they have results that you can approximate almost anything with one hidden layer, but then you don't have any explicit bounds that how wide, what is the dimension of the middle layer that you should require. Now when they consider deep neural networks, then there are very good results that you can somehow estimate both the depth and the width of neural networks that you are needed. Also in our paper with Wong and the Hoop, we also we were considering this kind of functions that imitate a kind of spectral theory that maps a linear operator to some other linear operator. So we take linear operators, for instance, polynomial operators or something we take a linear operator, then we consider some kind of spectral calculus, and then we can answer how well these neural networks that we consider how well they approximate like functions of operators that are defined in the sense of spectral theory. So we have some approximation results.
Thank you. Are there any further questions or comments? Okay, if not, let us thank Matti. Matti, thank you very much for the nice talk. And we still, if you would like to chat to your colleagues, please stay with us. Thank you.
Okay, thank you. I will now stop recording. Thank you very much for